In this figure, we can have an idea about how the atomic structure for these four elements. Silicon with 14 as its atomic number has 284 atomic structure, germanium 2818 and 4 atomic structure, arsenic 2818 and 4 atomic structure, and gallium 2818 and 3 atomic structure. In a pure silicon or germanium crystal, the 4 valence electrons of one atom form a bonding arrangement with 4 adjoining atoms. This bonding of atoms strengthened by the sharing of electrons is called covalent bonding. Since gallium arsenide is a compound semiconductor, there is sharing between two different atoms. The sharing between gallium arsenide is 5 electrons provided by the arsenic atom and 3 by the gallium atom. On the right-hand side is the covalent bonding of the silicon atom, while on the right is the covalent bonding for the gallium arsenide crystal. Covalent bond will result in a stronger bond between the valence electrons and their parent's atom. However, it is still possible for the valence electrons to absorb sufficient kinetic energy when any heat from external such as from surrounding medium can break the covalent bond. This will cause free state. This free state is referred to any electron that has separated from the fixed lattice structure. At room temperature there are approximately 1.5×10⁻10 free carriers in 1 cm³ of intrinsic silicon material, whereby these 15 billion electrons in a space is exactly smaller than small sugar cube. The free electrons are a material due only to external cause referred as intrinsic carriers. Interesting, the difference between the semiconductors and conductors is at their reaction to the heat application from external influence. For conductors, the resistance increases with an increase in heat. This ID due to number of carriers in a conductor do not increase significantly with temperature but their vibration pattern. However, the semiconductor materials exhibit an increased level of conductivity with the application of heat. Here, as the temperature rises, an increasing number of valence electrons absorb sufficient thermal energy to break covalent bond and contribute to the number of free carriers. Within the atomic structure of every isolated atom, there are specific energy levels associated with each shell and orbiting electron as shown in the figure on your right. The farther an electron is from the nucleus, the higher is the energy state, and any electron that has left its parent atom has a higher energy state than any electron in the atomic structure. Only specific energy levels can exist for the electrons in the atomic structure of an isolated atom. The result is a series of gaps between allowed energy levels where carriers are not permitted. Interaction between atoms results in an expansion of the fixed, discrete energy levels of the valence electrons of Figure 3A to bands as in Figure 3B. In this figure, we can understand and see the energy level, conduction, and valence bands of an insulator, a semiconductor, and a conductor. In this figure 3b, the gap of energy level for each of the three are explained well. we can see that an insulator has a big gap of energy level different on the left, while the conductor shows its small gap of energy level in the most right. These three arrows shows the region which is called the forbidden gap, or band gap e.g. This is the energy difference between the maximum valence band energy EV and the minimum conduction band energy EC. Between the two bands, which conduction and valence bands, there is an energy gap that the electron in this valence band must overcome to become a free carrier. The energy gap is different for germanium, silicon, and gallium arsenide. Germanium has the smallest gap and gallium arsenide has the largest gap. An electron in the valence band of silicon must absorb more energy than one in the valence band of germanium to become a free carrier. Similarly, an electron in the valence band of GaAs must gain more energy than one in silicon or germanium to enter the conduction band. This difference in energy gap requirements reveals the sensitivity of each type of semiconductor to changes in temperature.
Okay, thank you for watching the NMZH channel. So hopefully you guys enjoy and get the benefit knowledge from this video. Thank you. Assalamualaikum.